Welcome to lecture number 10 for EE206, Circuits 1, Thevenin Equivalent and Load Lines. Now what we've looked at so far are two techniques for solving a circuit. We can write the voltage node equations. There you guess the voltages at each node and find them so that the currents add up to zero or balance. We have a second approach, current loops. Find the currents in the equation or in the circuit so that the voltages balance. Here's the third tool. It's Thevenin Equivalents. It's a harder tool, it's more difficult to comprehend, and it's really not necessary. You can solve any circuit using voltage nodes and current loops. However, Thevenin Equivalents can make some circuit analysis much easier. It's used quite a bit in electronics. It helps understand how circuits works. So it is a useful tool. The idea behind Thevenin Equivalents deals with things called load lines. Now if I have a circuit like this, and I take the output, if I make the output an open circuit, I'll have some voltage. An open circuit would be right here. There's no current flow, and I have a voltage. As I change the voltage at the load and reduce it, the current goes up. And eventually, if I make the 0 volts, short it out, I'll have maximum current flow. That's at this point. Anywhere in between, the voltage and current then forms a straight line. That's called a load line. Another way to think of that is if I have a resistor right here. If the resistance is infinity, I'm right here, there's no current flow, I have a maximum voltage. If the resistor is 0, I have 0 voltage and maximum current. As I change the resistance between A and B, I move along the load line. Now, any circuit that has the same load line behaves the same way. So the idea behind Thevenin and Norton equivalents is what's the simplest circuit that gives me the same load line? And that would be a voltage source and a resistance. Here the open circuit voltage is on the x-axis, the voltage when the current is 0. The short circuit current, that's on the y-axis, is V Thevenin over R Thevenin. And then if I have a different point, just change the resistance between A and B, I'll get a different resistance and voltage, some spot on the load line. The other version is the Norton equivalent. Here if I short the output, short A and B, the current is I Norton, that's the current on the y-axis. If I have an open circuit voltage, I just get I times R. And any point in between, change the resistance between A and B, I'm some spot on the load line. So to find the parameters, V Thevenin, R Thevenin, I Norton, R Norton, there's basically 3 different tests you can run. What I like doing is refer back to these circuits. This is the equivalent to the circuit you're analyzing. What test would you run on the Thevenin equivalent to find the V Thevenin and R Thevenin, or equivalently, I Norton, R Norton? Do the same test on your circuit. You've got to get the same answer because, again, those two are equivalent. To find V Thevenin, what you do is measure the open circuit voltage. If it's open circuit, the current is 0, so I times R is 0. VAB equals V Thevenin. To find the short circuit current, or I Norton, you short the output, and I get V over R. Over here, short the output, I get I Norton. To find R Thevenin, turn off the source. V Thevenin goes to 0, and I just see a resistor. I Norton goes to 0. If the current is 0, I just have a resistor. So that's basically the idea. I need to find 2 parameters, come up with 2 different tests to find those 2 parameters, and there's 3 ways you can do it. As an example, here's a circuit. Find the Thevenin equivalent looking left at point A and B. To do that, I'll have to do 2 tests. Find the open circuit voltage, and then find the short circuit current, or turn off the sources and find the resistance. And we'll do each of those. To find the open circuit voltage, that's just a circuit like we've been doing. Here I'll do voltage nodes. This is 10 volts, this is V1. There's no current flow, so V out equals V1. Find V1 so that the currents balance. And that would just be the current left, V1 minus 10 over 5, plus the current down, V1 over 10, plus, actually minus 3 amps, equals 0. Solve and get V1 as 16.66 volts. That's the open circuit voltage. That must be V Thevenin. Next, find the short circuit current. To do that, I'll take the output and short it, and again, write a voltage node equation and solve, and I get V1 is 13.64 volts. The current then is 13.64 volts over 15 ohms, 0.909 amps. That's IA Norton. Third test is find our Thevenin. Turn off the current source, so this is open, 0 amps. Short the voltage source, this is 0 volts. And what I see is 15 ohms in series with 10 ohms in parallel with 5 ohms. Gives you 18.33 ohms. So that's the resistance, that's R Norton, that's also R Thevenin. So here's your Thevenin equivalent or the Norton equivalent. And note, I don't have to do all three. 18.33 ohms is also 16.67 volts divided by 0.909 milliamps, or the current is voltage over resistance. Find 2, that's all you need. With Thevenin and Norton, you can flip between the two. If I have a Thevenin equivalent, I can convert to a Norton. Likewise, if I have a Norton equivalent, I can convert to Thevenin. So I can simplify some circuits by flipping between Thevenins and Nortons. For example, in this circuit, here I've got a Thevenin equivalent, 10 volts and 5 ohms. Convert to a Norton. That becomes a current source and a resistor in parallel. The resistors in parallel add, current sources in parallel add, and then I can convert back and get to 15 ohms. So that'll be the idea. Starting out, 10 volts and 5 ohms, the Norton equivalent would be V over R, 2 amps, and the resistor stays the same. So there's my 2 amps and 5 ohms. I can now combine these, 5 in parallel with 10, and 2 in parallel with 3 gives you 5. Gives you 5 amps, 3.3 ohms. I can now take this, convert back to a Thevenin. The resistance will be the same, 3.33 ohms. The voltage is I times R. Gives you 16.66 volts. Now these two add in series, gives you 18.33 volts. So the Thevenin equivalent is 18.33 volts, 16.66 volts. So there you can see I was able to simplify a circuit by flipping between Thevenins and Nortons. An example of why you'd want to use Thevenins is this circuit. This is a case where I've got a voltage divider. It'll convert 12 volts down to 5 volts, but it only works if you don't use it. For example, if I built this circuit and measure the output voltage, I get 5 volts, so everything looks fine. If I connect it to a load that draws 100 milliamps at 5 volts, suddenly the voltage goes away. Why is that? Well, Thevenin is one way you can look at it to understand. Let's take the Thevenin equivalent to this circuit, looking left. The Thevenin voltage will be the open circuit voltage, 5/12 of 12 volts, or 5 volts. The Thevenin resistance is, turn off the voltage source, I've got 7K to ground in parallel with 5K to ground. So the Thevenin equivalent is this, 5 volts and 29/16 ohms. My load, 5 volts drawing 100 milliamps, looks like 50 ohms. When I connect a 50 ohm load to across the 50 ohms across the load, what happens is by voltage division, I get R1 over R1 plus R2. The voltage goes from 5 volts settling down to 0 volts. This output impedance is too large to drive 50 ohms, so likewise, it doesn't work. This is a DC to DC converter that works as long as you don't really use it. So likewise, you're getting 0.08 volts. There are ways to convert DC to DC. That's covered in EE206.10 Electronics 1. For this class, Circuits 1, where we're just starting out, this is just a voltage divider that is kind of lacking. There are better ways to do it, but that's not covered in this class. So that's lecture number 10, Thevenin Equivalents for EE206. Our next lecture will look at some more Thevenin equivalents, a little bit more complicated circuits.